Okay, this is the last in-person lecture. Sorry, Jonathan, you're the only person here. Yeah, if I see a major upswell of enthusiasm for more in-person activities, then we will then we can consider reinstating them. But it's not really worth it at this point when there's only 1 or 2 people that show up every week. Okay, mute yourself, please, Adrian. But let's go ahead and get on with the subject matter, unless there were questions about anything that's been going on in the class so far. I posted homework 4. Look out for, at some point, a poll to try and schedule an exam, which would be during week 7. I think right now we're on week either 4 or 5, if I'm not mistaken. So it'll be sometime at that point. I'll try and get feedback from everyone on when it would be the best to do it. We'll try and do as of now, we'll try and do a synchronous exam just over Zoom and stuff. That way, there are inevitably going to be questions during the exam because I usually write all the exams fresh. And I don't want to give anyone an unfair advantage having not, without being able to get real-time feedback on what's going on in the exam and any questions and stuff. Okay. Yeah, but as of now, let's go ahead and continue with the class material. This is where we were. This is what we introduced on Wednesday. This is called Stokes' first problem. The idea is that we have a flat plate sitting below an essentially infinite amount of fluid. And at time t equals 0, that plate is suddenly set in motion towards the right. These are the axes that you see over here. And then, by reducing the Navier-Stokes equations, specifically the x component, we're able to get an equation that looks like this, where nu is this kinematic viscosity. And those equations are governed by boundary conditions, 1 initial and 2 boundary conditions, because you have 1 derivative in time and 2 derivatives in position, right? And this was a little bit of a different beast than what we've seen in the past, or equations that we've solved so far in this class, because this is a partial differential equation, and so it requires some other solution methods to get there. Most of us, as a graduate class, most of us already know how to solve simple ordinary differential equations, but partial differential equations are maybe something that at least some of you might not have seen before, right? And so the solution method that we were going to use is something called the similarity solution. And the idea is that we're going to try and express our velocity, which we went ahead and non-dimensionalized using the u that's given in the problem, and express that in terms of a c variable. And that c is a combination, a special combination of our two independent variables, y and square root of 4 nu t. And if we get lucky, and I wouldn't be showing you guys this if we weren't going to get lucky, we can actually use this to simplify the equation down significantly into something that we can actually solve very easily. Okay, and so to do that, we were taking the 2 derivatives on either side of this equation here. This equation, this derivative here is df dt, and you just apply the chain rule to get to something that looks like this. And this d squared f dy squared, you just do the chain rule twice, and you get something that looks like this. Okay, and so then then the game is just going to be to take these 2 derivatives, this derivative here and this derivative here, and plug it into our solution, or plug it into our equation, and the boundary conditions, and see where this gets us. So let me go ahead and do that. The left-hand side is df dt, and so let me just write that down right now. df dt is 2 minus 2 nu y 4 nu t minus 3 halves. Someone please yell at me over Zoom if my sound cuts out, and do it as quickly as possible so we don't lose any time. Okay. The right-hand side is nu d squared f dy squared. So let me go ahead and do that here. I have a nu, and then I have 4 nu t to the minus 1 d squared f dc squared. Okay. This allows us to do a little bit of cancellation. The nu cancels out on both sides here, and then 1 factor of 4 nu t to the minus 1 cancels out. And so on the right-hand side, or on the left-hand side, I now have negative 2y 4 nu t to the minus 1/2 now. And then the right-hand side is actually just this. And if you look carefully at this, then you realize that y4 nu t to the minus 1/2 power is just my xc variable here. So I end up with an equation that looks like this. Okay. And this is kind of nice because, well, the purpose of introducing this complicated variable right here is that potentially we can simplify our equation. And what we did here is we took both our derivatives in t and derivatives in y, and we're able to cancel some stuff out, such that now f only depends on xc, right? And so now we've basically taken a partial differential equation, and all the derivatives now are in terms of xc, and so this becomes an ordinary differential equation. Okay. That's kind of cool because, like I said, we are good at solving ordinary differential equations, and I'll show you in just a second how we actually solve this particular one. Okay. There was a question during a lecture on Wednesday about why we added this 4 right here. The 4 is just so that we get a 2 over here. If you did not add the 4, that's totally fine. There might be like a square root of something or something like that, but the math is still essentially the same. It just makes it so I can write it a little bit more neatly at the end. Okay. For any sort of transformations that we do, we also have to consider the boundary conditions. So let's go ahead and look at the boundary conditions. The initial condition, let me write that down again. That was that at t equals 0, I'll write at t equals 0. Then we have that f equals 0.
You're cutting off.
Right. And that implies that at c goes to infinity. Says my battery still, is my battery, like, can you hear me? Hello? Can you hear me? Okay. I think that was an internet issue, not a microphone issue. I'm not sure why the internet was having an issue. Okay, we were talking about the initial condition here, right? The initial condition is that at t equals 0, f equals 0. Well, when t equals 0, if you look at the definition of xc, t equals 0 corresponds to when xc goes to infinity, right? And so we have, as c goes to infinity, then f equals 0. Okay. We have the two boundary conditions. Boundary condition 1 was that at y equals 0, f equals 1. This is the boundary condition that the plate is moving at a speed of u. Speed of u means f equals 1, and then at the plate, y equals 0, right? This implies when y is equal to 0, as you see from this definition, then c is equal to 0, right? And so this says that at c is equal to 0, f is equal to 1. Okay. Boundary condition 2 was that at y goes to infinity, let me draw a better infinity here, is equal to 0, right? Really, really far away from the plate. When y goes to infinity, we have 0 velocity. And that implies, again, right here, when y goes to infinity and for finite values of time, then c goes to infinity as well. Okay. So at c goes to infinity, f is equal to 0. And this is kind of cool, right? Because as you can see, the initial condition and the boundary condition 2 actually give us the same boundary condition now for c, right? And that's a prerequisite for this solution method to be successful. Because as we've talked about a little bit over the past couple lectures, when we try and solve an equation, for every derivative, you have to have one boundary condition. Okay, that's not only a necessary condition, it's also a sufficient condition, right? What that means is that if we have only two derivatives here, you should expect two boundary conditions. If you had a third boundary condition, then you actually would not be able to solve the problem. Your problem is actually overspecified, and you would not necessarily be able to find a solution that actually works out. Okay, but in this case, our original three boundary conditions actually collapse into two boundary conditions, right? So I'll just say original three boundary conditions collapse into two boundary conditions for C. This enables the similarity solution. Okay, and so now, given our differential equation and two boundary conditions, we can actually solve the ordinary, we can actually solve this equation now, right? And so let's go ahead and solve that. Okay, to solve this differential equation, those of you guys that have had me in class before and might remember this a little bit, you're not allowed to answer, but does anyone else have any idea on how to solve this particular equation? This is just a second order ordinary differential equation.
Can you just go to like a sheet with the solves generalized solution and plug in the?
Any ideas? The answer is no one.
Wait, can you hear me?
Can you say that again? I'm sorry.
Oh yes, can you just go to like there's like a equation sheet with the general.
Yeah, I can hear you. Can you say that again?
Can you hear me now? Oh no.
We can hear you.
I know you can hear me, but he can't.
Wait, I think his screen is frozen.
Yeah.
Might be internet stuff.
Either that or he got like sucked into cyberspace.
Oop.
Rip.
You really didn't like your answer.
Probably.
Call him Lindsay.
When the world needed him the most, he vanished.
Nikhil should teach us how to solve the equation.
Oh. I mean, couldn't you just like create like another variable and like say like y is equal to df dc, right? And then you're just saying dy dc then is equal to y times everything.
I'm back, I think. Can you hear? Can everyone see and hear me now? No? Yes? Yes.
We can.
Okay. Awesome. I was about to call in using my phone, but I don't know if that would have worked anyway. I heard the tail end of a discussion going on about, I think, the question that I was posing. What was was that discussion fruitful?
I mean, I was just thinking like, all right, we can convert a second order ODE into a first order ODE by saying, all right, we have y is equal, well, it's also linear, right? So we should be able to do this, right? So we have like y is equal to dfdc. And so we say, all right, dy dc is equal to 2c times y.
Exactly. That's exactly what the way that doesn't always work. If there were a term in here that said something 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 f, then you wouldn't be able to do that,
Okay.
right? Because then you'd have both an f and a y in there. But in this case, the lowest order derivative that we have is actually just df dc, right? And the highest order derivative is d squared f dc. So it's a second derivative and a first derivative. We have no zero order derivative, right? And so what we actually, this looks like a second order differential equation, but what we actually have is just a first order differential equation. And a first order differential equation is even easier to solve. We could do that, right? So let's go ahead and just do that conversion as Nikhil was talking about. I'm not going to use y, I'm going to use g, just because we use y for, you know, we actually have a y variable in our equation here. So df dc, like that. Okay. Then the ODE becomes this. As Nikhil was saying, minus 2 c times g equals dg dc. Okay? And now this differential equation, I think a lot of us can solve. I won't. We already lost a little bit of time on the hardware stuff. And so I'll go ahead and just mention how we would actually do this. You just separate, right? And so to separate, what you get is, let's say we multiply both sides by dc and then divide by g. So we get dg over g is equal to minus 2c dc, like that. And then integrate both sides. So you get log of g is equal to minus c squared plus some integration constant, I'll call that k1. And the reason I call it k1 is just because usually it's easier to express this like a g is equal to c1 times e to the minus c squared, where I just took the exponential of both sides. Okay. Cool, but again, we're not done because this tells us what df dc is. And so we just need to go one step further. We get that df, wow, that's a terrible d, dc is equal to c1 times e to the minus c squared. And so then we take an integral. The problem is that we actually can't take this integral. There's no solution to this integral, or there's no closed form of this integral. But I'll just express things like this. Here, instead of calling it a c, which gets confusing, I'll call this like s. Okay. Does that kind of make sense? Again, there's no closed form for this integral. I'm going to show you guys in a second what this integral actually is. There's actually a quick definition for it. But you know, you can just write like this. The way that you check is that this actually works. If you take a derivative of both sides, then you should get what you originally had. You can do that just using the second fundamental theorem of calculus. Okay. All right, now we need to apply the boundary conditions. Okay. It looks a little hairy, but it should be essentially the same as what we had before. Boundary condition 1 was that at c equals 0, f is equal to 1. Okay, and so what that implies, let me go ahead and write again, at c equals 0, what we have is, well, f is equal to 1, so we have 1 is equal to, if we plug in c equals 0 here, this integral is 0, because it goes from 0 to 0. And so then we just have c2. Right? Okay, boundary condition number 2. I'm throwing out my initial condition because it's telling me basically the same thing as boundary condition number 2. So I'm just going to write boundary condition 2 here. Okay. Boundary condition 2 is that at c goes to infinity, then f is equal to 0. So what we have is 0 is equal to c1 times integral from 0 to infinity of e to the minus s squared ds plus 1. I told you that there's no closed form for this integral in general. There actually is a closed form for this particular integral where specifically the limits go from 0 to infinity. Okay. If you haven't seen this sort of analysis before, you almost certainly are not going to guess what the value of this integral actually is. The value of this integral is square root of pi over 2. Okay. If anyone wants to stay after for a second after class, or is really curious how that actually came about, I can try and derive it in a second. Okay. But then this implies that C1 is equal to -2 over the square root of pi. Okay, and so what this implies then, now we actually have an expression for this. Let me just write in terms of, I can write in terms of f, but I could also write in terms of Vx. Remember, Vx is f times u. So u here now is just going to be 1 minus this expression. Okay. And it turns out that this integral right here is actually something that's so commonly seen that it has a name. This integral is called the error function. I don't know what's going on with my pen today, sorry. It's called the error function. Okay. You can look up what it actually looks like. It's basically just the integral of this e to the minus s squared, and this e to the minus x squared here is a Gaussian function, right? Real quick, the error function looks something like this. It looks something like this. The limits here are 1 and -1. Okay. But for other properties and stuff like that, just go on the internet and find it. Okay. In terms of, remember, we can plug in our similarity variable now at this point too. What we find is that Vx can be written like this. And this is just me plugging in the definition of C here. Okay. It turns out that 1 minus the error function is also so commonly seen that there's a special name for that too. And that's what we're going to use for the solution moving forward. There's a C here. This is called a complementary error function. Okay. And well, it's 1 minus this, and so you could see, or you could imagine, for instance, what this would actually look like. Sorry, I'll draw this a little better. It's just 1 minus this, and so instead of the limits going from the asymptotic limits going from -1 to 1, it now looks something like this, where it intersects the y-axis at 1, and it decreases from 2 down to 0. Okay, and this is perhaps not as, I guess, if you didn't know this a priori, you might have guessed that the function looks something like this. because as I mentioned, this is just the integral of a Gaussian function, a normal distribution basically, right, from 0 to whatever. And so if that whatever is positive, then you're going to have something that's positive, and if that whatever is negative, then you're going to have something that's negative. Kind of makes sense, right? Okay. We can plot what this actually looks like. If you stare at this sort of, that basically the velocity looks something like this over here, right? If I were to, for instance, draw this is my plate, it's moving to the right, okay? Here's my y-axis right here, but instead of plotting it versus y, I'm going to plot it versus square root of 4 nu t, like this. Then my expression looks something, then my velocity profile looks something like this. Okay. This is basically just me taking this side of this function and then just turning it so that it's actually moving in the direction of the velocity that I care about. Okay? What you see is that basically the velocity starts off at 1 or u, right? And then decays to 0 as this variable increases, just like how irc starts at 1 and decays to 0 as the argument of the irc increases. Okay. In practice, what we actually see is that like the x-axis of this variable, it goes from 1 to 2, et cetera. And then once the argument gets larger than 2 or so, then the values are essentially close to 0. I think the value is all the way at like when s is equal to like to 2, the y value here is something like 0.05 or something. It's starting to get really close to 0. Okay. Now, this is versus y, or this is versus y over square root of 4 nu t, because that's what's inside our little function here, right? But if we are interested in what happens with when we look at y, what we essentially see is, we want to plot it against y, is that what we have here is this length scale, square root of 4 nu t, right? Y divided by that gives me something that's unitless, and so therefore this variable right here has units of length, right? And this is basically a scale. You could think about this as a unit, if you will, right? You can think about this as a ruler. And when I take all of the, when I take sort of snapshots of my velocity profile with respect to time, and I rescale the units, like if I take various snapshots of it at various times, and then I rescale the y according to square root of 4 nu t, then they'll all collapse exactly on top of one another, and they'll look exactly like this, right? If I don't scale that, then what I see is basically, initially, my velocity profile might look something like this, right? But then as time increases, the scale gets larger and larger and larger. Okay. This is why my solution method here is called the similarity solution, because the shape of my velocity profile always looks exactly the same, but they're self-similar. So as time increases, it's as if my length scale just slowly increases over time. And that length scale increases as the square root of t. It works out because of the units too, right? Because the units of nu here is meter squared per second, length squared per time, right? So if I multiply by time and I take square root, then that gives me a length. Okay. So what we have is a self-similar velocity profile. Okay. The length scale increases with a square root of 4 nu t. As time increases. And that's generally how the similarity solution, like what the actual solution of these sorts of problems look like. That's sort of the major advance of Stokes' first problem, basically. Solving a partial differential equation and then getting a result where basically the velocity profile doesn't change really. It's just that, you know, if I were to rescale my system, if I were to zoom in or out, that's the same thing as if my time increases, basically. And you'll see this sort of length scale a lot in this type of problem. It's really common, basically. And it's just because in a lot of these sorts of equations, if you see a nu, that nu is a length squared per unit time, right? And so that length squared per unit time means that the best way of, or one of the only ways of making a length scale is square root of nu t, right? Basically, one of the only ways of combining those variables that gives me something that has units of length is square root of nu t like this. Okay? Okay. There's some other interesting observations to be had here. Okay. Do you guys remember what vorticity is? You guys just did homework number 3, right, where there were a few problems based on that. There are a few interesting observations with respect to that. Let me actually show you guys what I mean. Okay. We can look at how the vorticity actually changes in this particular problem as well. Okay. Vorticity, if you might recall, is just a field, just like a velocity field. You could define like a vorticity distribution or something, just like you would a velocity distribution and stuff. The vorticity is defined as the curl of the velocity, right? It basically tells you how much the velocity is well, curling, right? It tells you how much swirl, if you will, there is going on in your velocity profile. Okay, you can imagine that there is some sort of swirl going on in the velocity profile. Another way of thinking about velocity of vorticity is like if I were to take like a little windmill or like a pinwheel or something and put that in different locations in the fluid, the vorticity tells me how fast it's spinning. Okay, if I were to take a little pinwheel and put it at this point in the fluid, well, my fluid is going faster on the bottom than it is on the top, and so you might expect that it spins counterclockwise or something like that, right? And so over the next couple of minutes, I'm going to tell you guys a little bit about how the vorticity actually varies as we move throughout this fluid. Okay? In this particular case, we're looking at curl of v, but my velocity here is only confined to the xy plane, right? There's no z component. There's no variation in z, and there's no velocity in the z component either, right? And so in this particular case, what we might expect is that my vorticity is only going to have a component in the z direction because, well, my velocities and stuff are only happening in the x and y plane like this. And then, you know, by the right-hand rule or whatever, the vorticity is then going to be normal to that, to the axis of rotation, or it's going to be the axis of rotation is always going to be perpendicular to that. Okay. You can also show that mathematically. For instance, what this implies is that WZ is dVx, oh sorry, dVy dx minus dVx dy. If I were to write the other components of vorticity, Wx and Wy, you'll see immediately that those are all equal to 0. Okay, because they all have either derivatives in z or they have components of velocity. They either have vz or they have derivative of something with respect to z, and both of those things are always going to be 0. Okay, just for simplicity, I'm not going to write the wz because we only have vorticity in the z direction, so I'm just going to call it w. Okay. Now, in our particular problem right here, our w is equal to dvy dx, but there's no vy. We only have a vx here, right? And so that's also equal to 0. And so we have just minus dvy dx, or sorry, dvx dy. And this is because Vy is equal to 0. Okay. We're used to expressing everything up here in terms of our similarity variable C at this point. And so let me go ahead and do that. We can do the chain rule again. Right, you guys believe me when I write that for the chain rule? Okay. And now it's fairly simple to evaluate both of these derivatives right here, okay? dvx dxc is fairly straightforward. This is my vx, okay? And so if I wanted to take the derivative of this with respect to c, then that's just, well, I still have the u, and I still have the minus 2 over square root of pi, right? But then the derivative of this guy right here with respect to c is just e to the minus c squared, right? Second fundamental theorem of calculus. Okay. So this first term here is minus 2 square root of pi times u e to the minus c squared. Okay. And then dc dy, we actually evaluated like from the other day, but we can do that really easily right here. dc dy is just 1 over square root of 4 nu t, right? Okay. So let me just simplify this a little bit. Just me plugging in what the definition of xi is here, okay? All right. Does this distribution look familiar to any of you?
It looks like the normal distribution.
It looks like the normal distribution, right? It is in fact exactly a normal distribution. Now, a normal distribution has a sigma and a mean, right? A normal distribution has a mean that would be, the normal distribution will look like e to the minus y0 squared over whatever. The mean here is going to be 0, and the sigma is what's down here. It's the square root of this value right here, okay? For those of you that don't remember what the normal distribution looks like, let me just go ahead and plot out a few vorticity distributions at various moments in time. Okay. At short times, we get something that looks like this. In fact, at time t equals 0, it's actually just a spike. In math, we call that a delta function. Okay. And we'll talk a little bit more about delta functions and stuff later on in the class. Okay. But as time increases, you think about then almost like the sigma of this normal distribution increases. It gets fatter and fatter and fatter and fatter. And so it looks something like this. If I could draw a little better. Okay. Another place where you might have seen this is in a mass transfer class. And if not, there's a chance Professor Richards next term might talk a little bit more about this as well. What we have is basically a concentration of something that's very high initially at one particular point. Again, in math, you call that a delta function. And we're seeing how that concentration spreads out over time. Okay, that's essentially what we have here. We have our vorticity starts off like a spike, and that diffuses out over time. So I'll say the vorticity distribution is initially a large spike that diffuses out with time. It broadens, right? And the distributions are Gaussian at all times. Okay, I can maybe show you guys even more how this works, or I can maybe prove to you even more if you don't believe me. The total vorticity in our fluid well, to get that, you would basically just take the derivative, or sorry, take an integral over the entire fluid. Okay, I'm integrating as y goes from 0 to infinity, and I'm integrating as x goes from 0 to 1, because it's all the same in all directions in x, right? X is a horizontal direction, so I'm just saying, okay, let's just do it over like a 1 unit length or something. Okay. To integrate that, so I don't need to actually integrate over the x. I'm just integrating from 0 to 1, and there's no dependence on x, so let's not worry about that. Okay. To integrate this, you can just use I think in high school or whenever you learn calculus initially, you might have called that like a U substitution, right? I'll substitute in S is equal to y over square root of 4 nu t, right? It's looking kind of familiar to you guys at this point, probably, right? Well, then it turns out that dy is equal to ds times the square root of 4 nu t. Okay, so I can plug that into this integral right here. This integral now looks like this. Right? Because this guy right here is just s squared, and my dy now has a square root of 4 nu t coming out. That's ds square root of 4 nu t. That square root of nu t cancels with this square root of nu t. The 4 square root of that gives me this 2, and then I have the square root of pi on the bottom, and the u comes out in the front as well. Okay. Now, we said earlier what this integral actually is. This integral is just the square root of pi over 2. Okay. And so therefore, the total vorticity in our system here is just u. Now, don't worry too much about the u at this point. My point is just that the total vorticity doesn't change in our system. Okay, it's as if we have some fixed quantity of vorticity. It's all initially concentrated at y equals 0, and then it diffuses away from y equals 0. Okay, if you think about it, here's our velocity profile that we drew earlier, right? In this velocity profile, initially, at very short times, all the velocity is concentrated at the very surface, right? At the initial surface right here. And the effect of this sudden jump in velocity starts to move gradually into the fluid, and so that's why you have the self-similar velocity profile, right? The self-similar velocities. And you would totally expect then that perhaps the vorticity, which comes about it's almost like a shear stress, if you will, right? It comes about because you have fluids moving past one another. In other words, if I were to take a little pinwheel and put it like right here, I would have very high vorticity. But then at initial, at short times, if I were to put a little pinwheel over here, all the way up here, I would see nothing. It wouldn't rotate at all because the velocity hasn't even moved up there yet, right? And so at short times, all the velocity, all the action is happening at the very surface right here. And so my vorticity at the surface is very high. But then over long times, this velocity profile starts to gradually look a lot less steep. And so, my pinwheel isn't going to rotate as quickly anywhere. So that's sort of what physically shows me that allows me to believe this a little bit. Initially, I have very high vorticity, but it's concentrated at the surface here. But that kind of diffuses out and spreads out over time. It turns out that the total vorticity is actually preserved here. It's actually conserved. It's just equal to 0, or it's just equal to U right here. Okay. So the total vorticity is conserved. Okay. Not quite done with vorticity yet. There's another kind of cool way of thinking about this that I want you guys to think about. Okay. It turns out that I can also calculate the total vorticity in my system using Stokes' theorem. Right? Stokes' theorem says that the vorticity inside a surface I can calculate by looking at the field around the edges. Does that kind of ring a bell? I think you guys did a couple problems like this in homework 3, right? And so if I strategically draw my surface here, here's my little plate. Remember, at time t equals 0, this plate suddenly starts moving to the right. Okay, if I draw a surface that looks like this, okay. I have these little squiggly marks here because this is supposed to go all the way out up to infinity. Okay. And I'll say that, right here is where y equals 0. Again, up here is where y goes to infinity. I'll let the boundary here go from x equals 0 to x equals 1. Okay. If I wanted to calculate the total vorticity in this area here, that total vorticity, I could write it down. And in fact, this is exactly the same integral as what I wrote up here, right? Okay. But another way of calculating that vorticity is using Stokes' theorem. Okay? Because WZ here, well, WZ is just EZ dot W, and W is del dot V. You guys see how that works out? Please ask questions or please interrupt if this doesn't make any sense. Okay? This works out in this case because n here is just equal to EZ, right? Remember, in Stokes' theorem, it's the normal vector to that surface, right? And according to the right-hand rule, right? And so the normal vector here is just EZ. And so EZ dot del cross V is just WZ in this case, right? Well, by Stokes' theorem, this is equal to this. Okay. And it turns out that in this case, well, we actually already calculated this. This was up here. But if we pretend like we didn't know that a priori, okay, we can actually calculate the right-hand side of this very easily. The way we calculate this is a line integral. We go around the circle, right? Okay. Let's say there are 4 different parts of this circle, or 4 different parts of the surface. There's a 1 here, a 2, a 3, and a 4. Okay? Along 1, what we have is v dot, and what's our tangent vector in this along 1 right here? Any ideas? Jonathan in the room here said EX, right? Because it's just going in the positive X direction. I'll just say DS right here, okay? And then, of course, along 2, we have V dot EY now, right? And then I'll just go quickly to number 3. That's V dot negative EX. Negative EY. Yeah, right? And it turns out all of these integrals are really, really easy to evaluate, right? This guy right here is just Vx evaluated along this right here, right? Well, you know, this is at the surface of the plate. And by definition, the velocity at the surface of this plate is equal to u, right? And so this first integral here is just equal to u. And we're only integrating from 0 to 1, and so it's just u times 1. It's just equal to u, right? It turns out that all of these other integrals right here are also really easy to evaluate. This right here is v dot ey, which is just vy. There's no vy. There's no velocity in the y direction. Okay? This right here is v dot negative ex, and so that's minus vx. But we're out at y equals infinity, and that boundary condition said that this also has 0 velocity. So this is 0. And by the same logic for part 4 right here, this is also 0. So the total vorticity is equal to u. So by Stokes' theorem and just evaluating this right-hand side of the integral, we show that this total vorticity is equal to u. Right, we're able to confirm that. Using a completely different method by actually calculating what the vorticity would be also shows us that the vorticity is equal to u, but it's kind of nice that these two things actually agree. Okay. All right. The last thing, I guess I have just a couple more minutes left. The last thing I'll mention is just if we want to look at the force on the plate. As I mentioned, in fluid mechanics experiments, the easiest things to measure are like flow rates and forces and stuff, and those are things that we're interested in a lot, right? How much force is the fluid exerting on whatever and stuff like that, right? And so to do that, basically, you look at the shear stress at y equals 0. That is just tau yx. And you can calculate that using Newton's law of viscosity. There's another term in here plus dvy dx, but there's no vy, so we don't need to worry about that, right? And by basically taking a derivative like this, or taking a derivative of this velocity profile and stuff at y equals 0, you get something that looks like this. And I don't have enough time at this point to go through the actual math, but it's actually fairly straightforward, okay? And so the key here is just that, or the thing to notice right here is that the shear stress is infinite at t equals 0, right? Because our t here is on the denominator, and so when t is equal to 0, then this just goes to infinity. And that actually halfway makes sense, right? Because at t equals 0, our plate is suddenly set into motion, and so we have an infinite velocity gradient there, right? Right at the surface of the plate, the velocity is equal to 0, or is equal to u, and then immediately above that, the velocity is equal to 0, and so that's why you have an infinite force there. The velocity is discontinuous there, basically. And so our solution here might actually break down at exactly that one point t equals 0. Okay, any questions?
Is the reason as to why the sum of or the total vorticity of our system remains constant, is that like a consequence of the conservation of angular momentum or no?
Yes, sort of. A better way that I like to think about it is that vorticity comes about from basically shear forces. If you think about it, this expression right here for the shear stress, dVx dy, is essentially the same as this expression here for vorticity, right? And so at a time t equals 0, we're pushing the plate with some known force, and then that gets conserved throughout the entire thing.
Right.
Okay.
Right. Like only at t equals 0 you're applying the force, but then like afterwards you're not applying any. Like,
right, exactly.
Continuously applying force.
Yeah, yeah. And so that shear stress basically takes time to diffuse through the entire material.
I see. Okay.
Yeah, I mean, but I think there is something there to deal with angular momentum as well, but that's not typically how it's thought of in fluids because we don't typically even need to think about conservation of angular momentum. You know, the conservation of angular momentum gives us the fact that the shear stress is symmetric, and then that's sort of where that conversation ends. But it's good that we're thinking about this sort of vorticity stuff because later on, towards the week 7, 8, somewhere around there, we're actually going to think about how does vorticity actually move throughout the entire fluid. It looks a lot like a mass transfer problem in the same way that we talked about here, right? And by looking at how vorticity is transported throughout an entire fluid, it actually gives us some pretty important results when we deal with, particularly later on in the class when we start talking about inviscid flows and stuff like that.
And another question that I had was when we're taking the line integral for our control surface, why are we saying that b dot negative ex is equal to 0?
You mean for this third one right here?
Right.
Because the velocity is equal to 0. There's no velocity at y equals infinity.
Okay.
Yeah. And so it actually just happens to work out that for various reasons, in 2 and 4, the reason is just because the velocity is perpendicular to EY, to the tangent there, right? But in this particular one, it's actually just really, really high. Like you're really, really far away from the plate. And so your velocity is just equal to 0 anywhere.
I see. Okay. All right. Thank you.
Okay. Any other questions? All right. If not, I hope everyone has a good weekend. I'll see you guys on Monday.